You recall, excuse me, our original example, which was this system of equations, which gave us this matrix equation. This matrix equation gave us the matrix. From that matrix, we obtained this matrix with the eigenvalues lambda. We'll go through the details of how that occurred, but you should hopefully recall those. The matrix equation will have a solution for the function e to the lambda t times x, dependent on the condition that the determinant of a minus lambda I be 0. The determinant of this matrix is 0 if lambda equals 1 or lambda equals 7. These are our eigenvalues. We use these eigenvalues, plugging them back into the equation, to get two eigenvectors. And we combine the eigenvalues with the eigenvectors to form our solutions. Now, we've been over this in detail. We're going to look at it in a little more generality before we proceed to solve more general equations. And then we'll come back to this example and talk a little bit about the terminology we've developed and a little bit about a couple of theorems that we're going to develop in the process. This equation, matrix equation y prime equals some matrix times y, can be generalized. So the general form of the equation will be y prime equals ay, where y is a vector. In this case, we assume that y is some multiple e to the lambda t times a column vector. Now this column vector has n components, as opposed to the preceding example where we had only an x1 and x2, only two components. There's nothing that restricts this scheme that we developed earlier to vectors with only two components. Now, of course, if you have more than two components, then in order to multiply the vector by a square matrix A, the matrix has to have n rows and n columns. And we depict, or we represent, the e to the lambda t times this n vector as just e to the lambda t times x, the x vector having n components. We've already seen examples of this sort of thing, but just to formalize it, let's define it right here independently of our previous discussion. If y has this form, then I just paused to make the vector over the y a little more distinct. It might have almost looked like a y prime. Okay, so if y is this vector, then the derivative, all this being constant, is just lambda e to the lambda t, the derivative of e to the lambda t multiplied by this constant. So that our y prime is lambda e to the lambda t times the x vector. And that's then equal to a times this vector, e to the lambda t x. Now we can manipulate this equation very easily using properties of matrix multiplication that we've mentioned, and that, as mentioned, you need to review. First thing we do is we can factor out this constant. E to the lambda t is just a constant. Formally, we have an associative law that allows us to multiply a by the e to the lambda t. That multiplication, unlike matrix multiplication, remember e to the lambda t is just a single number for any value of t. Unlike matrix multiplication, that's commutative, so we can switch a and e to the lambda t. And then we can apply an associative law to group a with x, and now we've got e to the lambda t out in front. Having done that, we can divide both sides of the equation by e to the lambda t to get the, and we switch sides to get the matrix equation ax equals lambda x. Recalling again that x is a column vector. This is just the product of an n by n matrix with a column vector is equal to some multiple of that column vector. Now, x is the same as Ix, where I stands for the identity matrix, it's implicit that this is the n by n identity matrix because no other identity matrix would multiply a vector with n components. Then, pulling the same trick we did earlier, we can represent this as lambda I times x, the right-hand side, as lambda I times x, just basically using an associative law, which gives us this equation. Subtracting this from both sides, we get this ax minus the lambda ix equal to the zero vector, not the zero number, because this is a vector with n components. Ax will be a vector with n components, and lambda ix will be a vector with n components. So our vector over here has to have n components. This is a zero vector, a vector in which every component is 0. Then, using a distributive law that applies to matrix multiplication, we can factor out the x so that a minus lambda I times x is going to equal the 0 vector. And again, emphasizing that this 0 vector is just a vector that consists of n zeros. This x is a vector that consists of n values, and when we multiply it by a minus lambda I, we transform it. We get a series of multiples of these original x values, so that this product gives us n expressions, an n component vector with n different expressions, each being a linear combination of the original x1 through xn values, and that has to be equal to the 0 vector, so every component has to be equal to 0. That means that we have n linear equations in x1 through xn. And if we know the value of lambda, we can then solve those n linear equations for the x1 through xn. Now the question is, we do need to know the value of lambda. How do we get the value of lambda? This matrix equation would have a unique solution if the matrix A minus lambda I was invertible. However, if we can invert the matrix A minus lambda I, we would get the equation. So if A minus lambda I is invertible, we get the equation x equals the inverse of A minus lambda I multiplied by, I've got that times the x vector, and I need to correct that, so I'm going to go away for a second. The x vector I had here should be the 0 vector. If we invert this matrix, then x is going to be the inverse matrix times the 0 vector. Well, the inverse matrix, any matrix times the 0 vector, is going to give us the 0 vector. So that if this matrix is invertible, our solution x is just the 0 vector, and that doesn't give us any information at all that's helpful in solving this equation. We have to get an x vector that has numbers here that aren't all 0. So I say if our solution x is non-zero, which is what we need, we're stuck, we're dead in the water if that's not the case, then the A minus lambda I vector has to be non-invertible. Now, a vector's in A minus lambda I matrix has to be non-invertible. Okay? For a matrix to be invertible, well, a matrix is invertible if and only if its determinant is non-zero, which means that the matrix is non-invertible provided its determinant is equal to 0. Okay, so we have the condition that the determinant of this A minus lambda I matrix has to be 0. Now, the determinant of the A minus lambda I matrix, as we've seen through examples, we know that to be a polynomial in lambda. If this is an n by n matrix, then that polynomial is going to be of degree n. Because, as you recall, whatever the diagonal elements of the matrix A are, we form this matrix by subtracting lambda from every diagonal element. So if we multiply all those diagonal elements, we have n linear factors, each equal to, or each being linear in lambda. If we multiply n factors, each of which is a linear function of lambda, we get an nth degree polynomial. Now I'll digress just for a second, or progress just a little further. We know that an nth degree polynomial in lambda has n solutions. Those solutions could be real, they could be complex conjugate, they could be repeated, they could be of any in any combination thereof. But we do know that there are n solutions to setting that polynomial equal to 0. So the determinant a minus lambda I gives us a polynomial with n solutions. Every one of those solutions gives us a different set of equations. A minus lambda I times the x vector equals the 0 vector. So every different value of lambda gives us a different system of equations. But in any case, every solution for lambda does give us n linear equations in x1 through xn. So that we have at least the potential to get n different solutions for the x vector. So there are n possible solutions for x vectors. Now if we have repeated solutions, complex conjugate solutions, etc., well, things don't get too complicated with complex conjugate solutions. With repeated solutions, they do get a little bit complicated here, but we see the scheme of things. We get a degree n polynomial with n solutions for lambda. Some of them might be the same. That gives us n linear equations in x1 through xn. And each independent set of linear equations is going to give us a solution for x1 through xn, which gives us an x vector that can be combined with the e to the lambda t vector for that particular eigenvalue, that particular value of lambda.